Welcome to the next lecture of heat exchanger and mass transfer. We saw conduction, convection, radiation modes of heat transfer in the previous lecture. In this lecture, we will try to see what are heat exchangers. There are different type of heat exchangers, shell and tube heat exchanger. What is heat exchanger? By the word itself you can understand there is an exchange of heat. It can be between two fluids, between the fluid and the surrounding. There is an exchange. The exchange can be higher to lower temperature or lower to higher temperature, whatever it is. So, heat exchanger, shell and tube heat exchanger, shell and coil heat exchanger, then pipe and pipe heat exchanger, plate type heat exchanger, boiling and condensation, boiling heat transfer, then condensation heat transfer. Finally, we will try to see the mass transfer. Heat exchangers. As I told you, heat exchanger, from the name itself it is very clear, there is a exchange of temperature. A heat exchanger is a piece of equipment built for efficient heat transfer from one medium to the another. The medium can be liquid, the medium can be air. So, here this is passed through a tube inside which a working fluid is passed through, right? It is passed through and then you try to take it out through the cooler side. So, here through which you can pass through a working fluid, or you can try to have a working fluid outside and the gas can be used to reduce the temperature. That is also possible. So, the working fluid can be here, or the working fluid can be here, and the working fluid can be gas or liquid, and here the outside can be gas or liquid, whatever it is you need can be, right. So, this is the equipment. You send cooler before, so then you have all the fluid flowing through, then hot before. So, you start from here, you push it through it. So, then when the cold air is passed by, the hot air is removed from the other side. It can be used as a heater, where in which the hot air is blown into the room. So, you get a warm effect. The media may be separated by a solid wall to prevent mixing, or they may be in direct contact. So, the fluid, working fluid can be going inside a tube or it can be outside. They do not want these two to mix, that is why they have a tube. The media may be separated by a solid wall. So, pipe is a solid wall to prevent mixing, or they may be in direct contact. They are widely used in refrigeration, right, air conditioning, power plant, chemical plant, petroleum chemical plant, petroleum refinery, natural gas processing and sewage treatment. Almost in every place they use these heat exchangers, wherever they wanted to exchange temperatures between working fluid and the surrounding. The classical example of heat exchanger is found in an internal combustion engine, IC engine, in which a circulating fluid cools the engine by a flow of a coolant through radiator coil. See, nowadays you do not see that impact. Before 10 years, you can see when you go on a highway, after every 100 kilometers or every 200 kilometers, people used to stop their vehicle, open the radiator on a hot sunny day and start pouring water into it. So, now they have changed the working fluid. They have changed the working fluid from water to an oil based. So, here what happens? The conductivity is reduced. So, once the conductivity is reduced, so the water does not boil. In the radiator nowadays you do not see boiling water coming out. So, the internal combustion engine, in which circulating fluid known as engine coolant flows through the radiator coil and the air is passed through the coil, which cools the coolant and heats the incoming air. The heat exchanger, classification of a heat exchanger by flow configuration. There are 4 types of flow configuration: counter flow, you can have concurrent flow, you can have cross flow, you can have hybrid flow, which is hybrid between cross control flow and multi-pass flow. These are different types of flow configurations. Heat exchangers. The topic itself clearly tells about heat getting exchanged. How will you do that heat exchanger? When you have a very large surface, the heat can get exhausted, or you can try to flow 2 different fluids in a pipe. So, this is one fluid and the other one is fluid 2. So, wherever you have a gradient T, then you can try to exchange, remove heat. That is why it is called as heat exchanger. So, counter flow heat exchanger. As its name says counter, that means to say it has opposite, counter, right? Counter flow heat exchange. In a counter flow heat exchanger, the hot and cold fluids flow in opposite direction. So, this one fluid flows here, the other fluid flows here. If the delta T is very small, then exchange takes a longer time. Generally, what we do is we try to reduce the temperature here and try to send a hot one here, but there also you can't have a steep dt. So, there has to be a small constraint on this. The dt need not be small, but there has to be within a range. Keep that in mind. The hot fluid enters from one side and the cold fluid enters from the opposite side, and they pass through. As and when they move, there is a heat exchange happening. So, notice the arrow direction in the figure given. So, one direction, two direction, fluid 1, fluid 2, right. So, when you try to plot it in a temperature versus length plot, you can see here this is the hot inlet and this is the hot outlet. So, hot inlet, you will see there is a fall in temperature when it goes out of the hot. Then the cold one, you see it increases the temperature. Next one is called as concurrent flow heat exchanger. Concurrent means both flowing in the same direction, right. So, here in concurrent flow, also known as parallel flow, the heat exchanger, both hot and cold flow in the same direction. So, you see here it is also flowing this way and it is exhausted this way. So, here it is flowing through this way and it is exhausted through this way. So, here it is fluid 1 and fluid 2. Friends, this can be cold, the outer can be hot, or the outer can be hot and inner can be cold. They enter the exchanger at one end and exit on the opposite side, one end entry and opposite side entry, moving alongside each other. So, it makes sure doubly that it flows like this, as indicated in the arrow in the figure. So, entry, exit. Friends, you can also change the Q. You can also change the flow. For example, here it is flowing at 1 Q rate. So, let us make it Q rate as 1. This will flow at Q rate as 2. Again, you can have a difference in heat exchange. So, when you try to see parallel flow, you plot it between temperature and length. You see here this is the inlet and this is the outlet. How is the inlet varying with respect to outlet for hot as well as for cold? By understanding heat exchangers, these two, you will be able to appreciate the use of these heat exchangers. These heat exchangers are used in engine, in automotive engines, in your air conditions, right, in boilers, in your aeroplanes, in your fighter planes, right, you use heat exchanger. So, I am by going through this, I am sure you will now try to understand why are these fin like structures given in a air conditioned unit. The next one is cross flow heat exchanger. The cross flow heat exchanger is a type of heat exchanger in which the hot and the cold fluid, so this can be hot and the cold fluid flow perpendicular to each other. One fluid flows through a set of tubes, these are tubes, or channel. This can be tube or it can be a channel. When I try to take a cross section, it can be like this. It can be like this channel, right? Which channel, if you want to visualize, it can be something like this. Okay. This channel, it can be tapered, it can be straight. Depending upon your requirements, it can have a taper, positive taper, it can have a negative taper, whatever it is. It can also have like pipes. These are pipes or tubes, right? One fluid flows through a set of tubes or channel, while the other fluid flows across them at 90 degrees at right angle. This arrangement allows efficient heat transfer and is commonly used when one fluid changes phase, such as air-cooled condenser or radiator. Right? When one of the fluid changes phase can be three phase, it can be liquid phase or gas phase. So, it can be liquid to steam or steam to liquid. So, the classifications of heat exchanger by construction can be: heat exchanger can be basically classified into regenerative, recuperative. Recuperative again can be classified as indirect, direct and special. Regenerative can be static or dynamic. In the sub classification of dynamic, you can try to have reciprocating or rotating. The regenerative heat exchanger works in the principle of piston or in terms of a pump. So, dynamic can be reciprocating or rotary. When we try to look at recuperative, it is indirect is tubular and plate, where direct you will have cooling towers. Cooling towers which you see just besides the mall, where there is a HVAC system, you will have a cooling tower. Cooling tower, direct contact condenser, steam instigator, direct heating. So, all these things are direct. Special type are scarred surface, wet surface and air cooled surface are part of the special classification of heat exchangers. We will try to see tubular. So, this is exchange by classification. Then we are trying to see in indirect tubular. So, classification of heat exchanger by construction tubular, you can have shell and tube structure, furnace structure, tube in plate, electric heating, air cooled and specialized type. In specialized types, we have heat pipes, agitated vessels, graphite blocks and bayonet. So, these are all special type tubular construction heat exchangers, but shell and tube, tube in plate, these are all very common. So, plate exchangers, tube in plate, when you see here plate, we are always talking about recuperative, indirect, tubular and plate. So, plate exchanger can be plate and frame, plate and fin, lamellae and spiral. So, again plate and frame can be classified as gasketed and welded. So, the recuperative heat exchanger has separate flow path for each fluid and fluid flow simultaneously through the exchanger, exchanging heat across the wall separating the flow pipe. So, basically it is separated by a flow path for each fluid, and the fluid flows simultaneously through a heat exchanger exchanging heat across the walls. Regenerative heat exchangers has a single flow path, separate flow path. Here it has a single flow path which the hot and the cold fluid alternatively passes through. Hot and cold fluid alternatively passes through. In regenerative heat exchangers, the flow path normally consists of matrix. In regenerative, they have a flow path normally consisting of a matrix which is heated when the hot fluid passes through. It is known as hot blow. The heat is then released to the cold fluid when this flow through the matrix happens. That is called as cold blow. So, you have a hot blow and cold blow in regenerative heat exchangers. This is a typical shell and tube heat exchangers, wherein which it consists of a series of tubes. So, these are tubes, small ones, these are all tubes. This is kept inside a shell. This is kept inside a shell. If you see a boiler, it will be like this. So, this will be assuming that this is the shell of the boiler. This is a boiler. So, here you have, this is the thickness of the shell. This is the shell. When you try to take a cross section, this is the shell, right. Inside the shell, you will see several tubes. This is a front view, this is a side view, you will see tubes. So, these tubes have to be held in the position. So, that is done by baffles. So, baffle will be again a plate wherein which it will have several holes in it. So, the pipes will pass through the baffle. So, if you see here, from here to here it passes, it tries to hold these pipes, then from here to here it holds here. So, it tries to hold the pipes in their regular position. So, this is held by baffles, shell, tube, baffle, right. Then you will try to see there is a shell side fluid in, there is a fluid which goes, and then there is a fluid which goes through the pipes. So, the shell side fluid in can be air or it can be water, and here inside the tube again it can be air or water or any other fluid. So, the tube side in fluid goes through this way, and from here to here when it flows through, it tries to do a heat exchange with the shell inside fluid in, with that fluid in. So, this straight tube heat exchanger is working on a principle of one pass. One set of these tubes consists of fluid that must be either heated or cooled. So, anything can flow through the fluid, the working fluid condition can be anything. The second fluid runs over the tubes that are being heated or cooled. So, the tube on top of the tube whatever goes. So, it can be heated or cooled so that it can either provide a heat or absorb the heat required. The set of tube is called as a tube bundle. So, there are many tubes. So, each of them are called as a bundle and can be made up to several types of tubes, plain, longitudinal, fin, etc., etc. So, it can be plain, it can be straight, it can be serpentile pattern also, it can be there. So, we can have many things. The shell and the tube heat exchangers are typically used for high pressure applications where we talk about 30 bar. And the temperatures can go up to 260 degrees Celsius. This is basically used in thermal power plants. This is because the shell and the tube exchangers are robust due to their shape. So, these pressures, 30 bar pressure inside a cylinder is not a big deal, and a 260 degrees Celsius operation is also not a big deal if using a steel material. So, the application of this, this is what I said, baffle. So, in the baffle you will see all the tubes which are attached. So, this can be in and this can be out. The simple design of shell and tube exchange makes it an ideal cooling solution for a wide variety of application. One of the most common application is the cooling of hydraulic fluid and oil in the engine, transmission and hydraulic power packs wherever they use this shell and tube type heat exchanger. With the right choice of material, they can be used to cool or heat through medium such as swimming pool, water or charge air. So, you can try to do anything. One of the biggest advantage of using shell and tube heat exchanger is that they are often easy to service, particularly with models where a floating tube bundle is available. So, for example, after a period of time, the tube can be choked. The fluid on the top which flows, that can deposit salts on it. So, it is also required to do maintenance. So, shell and tube type exchangers are very easy for it. The shell and coil, this is shell and tube. The next one what we are doing is shell and coil. Coil is it goes around. So, there is a fluid in the center, there is a coil. So, you can see the fluid and then there is a coil. Shell and a coil heat exchanger are constructed using circular layered of helical corrugated tubes placed inside a light compact shell. And friends, when we try to talk about this, the coil, whatever is there, and on top of the coil, if you try to have, suppose let us assume this is a coil. This is a coil. So, now what we can do, we can also have projections on these coils. So, what is the advantage of these projections? These projections are going to have a larger surface area on the coil. So, there is going to be more heat extracted from the fluid through this coil. So, you can have rivets which are welded, short, and it is welded on top of the coil. So, the fluid in each layer flows in the opposite direction to the layer surrounding it, producing a crisscross pattern. So, crisscross pattern. The large number of closely packed tubes create a significant heat transfer surface within a tight compact shell. Friends, this heat exchange, if it has to happen, you can always have a heat exchanger. But the size of the heat exchanger is also very important, because many a times these heat exchangers will be attached to a moving body. If it is for a static one, the sizes do not matter. But if it is placed inside an automobile, if it is placed inside a car for AC, right, or if it is placed inside a rocket which goes. So, there the compaction is also very important. So, light compact shells are very important. The alternative layers create a swift uniform heating of fluid, increasing the total heat transfer coefficient. So, the swift uniform heating of the fluid. So, this you have to go here when the heat exchange happens, you should remember the things what we studied for convection. The fluid is flowing on top of it, the thickness of the fluid plays a role, there can be a vortex which is created. So, all these things can take place. So, the other thing is the corrugated tube. The corrugation is you have a surface area increase, corrugation is this. The corrugated tubes produce a turbulent flow where the desired feature of the fluid velocities are achieved. So, the lamellar flow is disturbed when you have undulations on the surface. So, that creates a turbulent and there is a heat exchange. So, the shell and the coil design is perfect choice wherever the high heat transfer rate, compact design and low maintenance cost are priorities. So, the benefits are going to be high performance, compact and lightweight, low maintenance cost are going to be the benefit of shell and coil type heat exchanger. It is the installation cost is very low. So, this is a typical one. You can see red is hot and the cold one is blue. So, and then you can see the coil which goes around. High temperature differentiation differentials can be achieved. Flexible device and low pressure drops are also seen. The shell and coil applications are finding lot of applications in heating systems, chilling water systems, groundwater systems, residential use. We use exhaustively shell and coil heat exchanger. So, this is a steam from a boiler which goes through it. The steam returns to the boiler. From the boiler, the steam returns to the boiler, and here there is cold water which is passed, there is a heat transfer which is happening. So, then it is pipe in pipe heat exchangers. So, pipe in pipe is, so you have a shell side fluid which flows inside a pipe, then there is a pipe which is inside, so which is called as the tube side flow out and tube side flow in. So, this is shell side fluid in, shell side fluid out, and these pipes are held between flanges. So, you have a flange to hold. So, double pipe heat exchange is one of the simplest form of shell tube heat exchanger. Here just one pipe inside another large pipe. There is only one pipe inside another large pipe. To make a unit very compact, the arrangement is made multiple times and continuous series and parallel flow. One fluid flows through the surrounded by pipe and the other flows through the annulus between the two pipes. So, the wall of the inner pipe is the heat transfer surface. This is called as a hairpin heat exchanger. The major disadvantages of pipe in pipe heat exchangers are The two most noticeable being the high cost in proportion to the heat transfer area. Plate type heat exchanger. These plate type heat exchanger you can see in room heat exchangers, which we use during winter days. A plate type heat exchanger consists of a series of thin corrugated metal pipes. So, these are plates. So, this is consists of a thin corrugated metal plate. So, these are all corrugated, these plates. Between the number of channels are formed with the primary and the secondary fluid flowing through it. So, this is a product which comes out, this is the steam which goes. So, primary and the secondary fluid flowing through them alternatively. The heat exchange takes place from the primary fluid to the secondary fluid in the adjacent channel across the plate. The figure shows a schematic representation of the heat pipes. Consists of number of plates arranged between the pressure and the fixed frame. The plates are having corrugation with different design, which increases the total surface area of heat exchange. The plates can be static, the plates can be movable. Depending upon the arrangement, they try to get the benefits. The fixed and the pressure plates are supported by the supporting column. The plates are fitted with each other with gaskets, which seals the material from coming outside ways as well as through the holes of the plates. The application of plate type heat exchangers are power generation application in food, dairy and brewing industry. It is there. Refrigerant in cooling systems are also having plate type heat exchangers. So, this is a typical plate type heat exchangers. You can have moving pressure plates, upper carrying bar and lower carrying bar. Upper carrying bar and lower carrying bar are to guide them. Boiling and condensation. Boiling and condensation are essential phase change processes. Boiling is from liquid to gas. Condensation is from gas to liquid. Boiling and condensation are essential phase change processes in thermodynamics involving the transformation between liquid and vapor states. The boiling occurs when liquid is heated to its saturation temperature, leading to the formation of vapor bubble within the liquid or on the heated surface. That is why when you try to heat a pan, in a pan you put water or milk. When you try to heat it from the bottom, you will see there are vapor bubbles which are formed on the top. So, the liquid is heated to its saturation temperature, leading to the formation of a vapor bubble within the liquid or on a heated surface. It plays a vital role in heat transfer system like boiler and evaporator, especially in the nucleating boiling regime, where heat transfer is highly efficient. So, you should understand this point. The heat transfer system like boiler and evaporator, especially in the nucleated boiling regime. When there is a nucleated boiling regime is there, it tries to vapor comes and then it tries to do a high heat transfer. On the other hand, condensation is a process where vapor cools and changes back to liquid, releasing latent heat in the process. If you go back to solidification, latent heat is playing a very important role. It typically occurs on cooler surfaces and can happen in the form of a film condensation, where a continuous liquid layer forms. It typically occurs on cooler surfaces, right, on cooler surface, and can happen in the form of film condensation. So, what happens is, when you have the relative humidity very high and you have a pipe wherein which you are passing cold air, what happens? This relative humidity air comes and hits at the cold air pipe and tries to form, it tries to condense, droplet gets condensed, and once the droplet gets condensed, it forms a film. It typically occurs on a cold surface inside a room, and can happen in the formation of film condensation, where a continuous liquid layer is formed, or a drop-wise condensation happens, which offers better heat transfer. So, here heat transfer is because of the nucleating boiling regime, and here it is because of the film condensation or drop-wise condensation. So, evaporation occurs at a liquid vapor interface where the vapor pressure is less than the saturation pressure of a liquid at a given temperature. Boiling occurs at a solid liquid interface. Evaporation is liquid vapor interface. Liquid vapor. Boiling occurs solid liquid interface, where the liquid is brought in contact with the surface maintained at a temperature sufficiently above the saturation temperature of the liquid. So, you see here this is the pan, so where in which you have a heater which is used. So, immersion heater rod. So, the solid liquid interface, when the liquid is brought in contact with the surface at a temperature, at the main temperature sufficiently above the saturation temperature of the liquid, boiling happens. So, these are all boiling. Bubbles are formed, boiling happens. When you talk about evaporation, the vapor pressure must be lesser than the saturation pressure of the liquid. So, the boiling heat flux from a solid surface to a liquid can be derived by this or can be obtained by this formula. Q boiling is nothing but enthalpy into Ts minus T saturated, which is nothing but H delta T excess in watt per meter square. The T excess is nothing but Ts minus T saturation. The classification of boiling can be done as it is called as pool boiling. In the absence of bulk fluid flow, there is a pool boiling effect. Any motion of the fluid is due to the natural convection current and the motion of the bubbles under the influence of the buoyancy. Under the influence of the buoyancy, this is there. The boiling is called as a flow boiling in the presence of a bulk fluid flow. In the absence of a bulk fluid flow, it is called as pool boiling. This is pool boiling. In the absence of a bulk fluid flow, it is called as pool boiling, and when there is a flow happening, it is called as flow boiling, where the presence of a bulk fluid is flowing. So, this is the difference between pool boiling and flow boiling. Friends, these are very important. In flow boiling, the fluid is forced to move in a heated pipe over a surface by external means such as a pump. The fluid is allowed to move through a pressure, right. So, this is called as flow boiling and this is called as pool boiling. There is something called as subcooled boiling and saturated boiling. Subcooled boiling is when the temperature of the main body of the liquid is below the saturation temperature. It is called as subcooled boiling. So, when the temperature at the base is 107 degrees Celsius and the liquid is around about 80 degrees Celsius, it is called as supercooled boiling. And the atmosphere is 1. Saturated boiling is when the temperature of the liquid is equal to the saturation temperature. So, here saturation temperature is very important. So, we saw what is pool boiling, what is flow boiling, what is subcooled boiling and what is saturated boiling. Friends, these are very important because you have to choose the regime through which the heat transfer can happen. So, when we go little deeper into pool boiling, in pool boiling the fluid is not forced to flow by a mover such as a pump. So, it is a static one in a pressure cooker where water is filled. Any motion of the fluid is due to natural convection here. Natural convection current and the motion of the bubble is under the influence of buoyancy. So, under buoyancy it can go up. So, Q boiling is nothing but it is expressed as T H into delta T excess. So, boiling takes different form depending upon the Ts. So, here it is natural convection and here it is nucleated boiling and here it is transition boiling and here it is heat and thin film boiling. So, you see here how many different boilings we saw. We saw pool boiling, forced boiling, supercooled boiling, saturated boiling, then we saw natural convection boiling, then nucleated. Nucleated means the temperature is slightly high, so there are nucleation of bubbles getting formed. Nucleated boiling, then we will try to have transition boiling and then finally we will have film boiling. So, all these things are different types of boiling which can happen. So, if you try to draw a boiling heat transfer, So, you can try to have 4 major regimes. So, one is called as natural convection boiling. So, where the Q boiling watt per meter square you can see, and delta exceed, which you can see in terms of temperature. So, here it is 1, where delta T we are seeing, right. We are seeing delta T. So, 5, 10, 30, 100, 120 and 1000, right. So, when it goes between 1 to 5, and when the watts Q boiling, let us assume it is 10 to the power 4. So, then watt per meter square, you can see a point A. So, in point A will be, you can see that here the bubbles are getting formed. So, then the bubbles collapse in the liquid is happening here till B. So, then the bubbles will try to rise to the free surface from B to C. At the C, there is a transition boiling. So, the maximum critical temperature heat flux will be Q max at this point. Then after this transition boiling, there will be a drop. There will be a drop. So, here the vapor pockets are getting formed up to D. Then D is the Leidenfrost point Q min, which is there before it goes to E. So, you can see here natural convection happening up to 5 here, that is delta T excess. Then C happening up to 30, where in which nucleated boiling is happening. So, first is just it goes like this thing, natural convection. Next, the bubbles are getting formed. The formed bubbles are rising from the bottom to the top. Then once it is rising to the top, then what happens is there is a transition boiling which happens. From there it falls down. The Q boiling falls down. So, the vapors go up. Then the vapors form a film. So, film boiling happens. This figure is very important, friends. This is a typical curve at only 1 atmosphere pressure you can do. If you can change the atmospheric condition, the entire thing changes. So, the natural convection is region A to B. In the first region A to B, of the boiling curve, the liquid is heated slowly and the surface temperature is only slightly higher than the saturation temperature. So, which is by 1 to 5 degrees. So, there is this regime of natural convection boiling, although technically no actual boiling takes place, the bubbles are getting formed. Then between B to C, when the surface temperature increases to a moderate excess temperature, the system enters the nucleated boiling regime. So, 30 degrees more if it increase. So, that is what we said, 30 degrees, right, 10 degrees to 30 degrees. This is the most efficient and a highly desirable region for boiling water. So, it is B to C. This is B to C is the most required regime. The vapor bubbles form at discrete nucleation sites. They are not forming at continuous sites. They form here, discrete nucleation sites of the heated surface and grow and detach to rise to the liquid. So, the boiling vapor will happen here. Then they will all move up. The departed balloon induce strong liquid mixing and turbulence when it goes to the top, and then it bursts, which significantly enhances the convective heat transfer. Then from C to D, you can see here, this is called as the transition boiling. Beyond the point C, the further increase of the temperature causes the onset of boiling, representing the regime C to D. So, here the onset of transition boiling happens. This is a highly unstable and inefficient region where the heat transfer decreases despite. So, here the heat transfer decreases despite the temperature increase. The heat flux drops steeply due to the formation of intermittent vapor films or pockets that temporarily blanket around the heated surface. So, here in this transition boiling, what happens? The temperature goes on high. So, now the vapor forms a jacket on top of it. So, the heat flux drops steeply due to the formation of intermittent vapor films or pockets that temporarily blankets portions of the heat surface. Then in D to E, whatever is that temporary one forms a regime. When the surface temperature increases significantly above the Leidenfrost point, a continuous and a stable vapor film is formed entirely. So, here the vapor film is not continuously formed. Here if you see there, the vapor film is not continuously formed, it forms here and there, but here in the film boiling it is completely formed, and that is the vapor being poor thermal conductivity acts as an insulating barrier between the surface and the bulk liquid, and here the Q increases. So, enhancement of heat transfer in pool boiling, this is very important. The rate of heat transfer in the nucleated boiling regime, liquid, this is vapor, this is nucleated site for vapor, you can see. The rate of heat transfer in the nucleate boiling regime strongly depends on the number of active nucleation sites on the surface and the rate of bubble formation at each site. Therefore, modification that enhances the nucleation, these are nucleation, on the heated surface surface will also enhance the heat transfer. So, liquid, vapor, so this is vapor and these are nucleated sites. Right. So, here therefore, modification that enhances nucleation on the heating surface will also enhance the heat transfer in the nucleated boiling. Irregularities on the heating surface including roughness, dirt will all be a possibility for a nucleation site formation. The effect of surface roughness is absorbed to decay with respect to time. So, flow boiling, these are all part of pool boiling. So, now we will try to see what is flow boiling. In flow boiling, the fluid is forced to move by an external force such as a pump is used. So, all these things are what we saw was not, we were seeing here was all pool boiling, because here we saw there are different types, right? Pool boiling, flow boiling. So, now we will try to, we saw what is pool boiling and we saw all the regimes of pool boiling: natural convection, nucleation phase, transition and film boiling. Now, when we go to forced boiling or flow boiling, the fluid is forced to move by an external source such as pump as it undergoes a phase change process. It exhibits a combined effect of convection and pool boiling. External flow boiling over a plate or a cylinder is similar to pool boiling, but the addition motion increases both the nucleation boiling heat flux and maximum heat flux considerably. So, the higher the velocity, the higher is the nucleation boiling. So, if you keep pumping it very fast, so nucleation boiling heat flux will also be very high. The internal flow boiling is commonly known as two-phase flow. In much more complicated in nature, because there is no surface for the vapor to escape, and thus both liquid and vapor are forced to flow through. So, this is called as flow boiling. So, here you can see what is the Q dot. What is Q dot? We saw here Q dot boiling, watt per meter square. So, Q dot is here and this is delta T in terms of excess. Delta T is the temperature difference in excess. Free convection you can see here, it moves from here and then there is a slope here and then it hits a Q max. So, this slope is nothing but nucleated pool boiling regime happens in this and then it hits a maximum. So, when we move at low velocity, this is free convection, pool boiling, this is flow boiling. Low velocity, high velocity, you can see here the Q max increases and it is getting shifted. The effect of forced convection on external flow boiling of different flow velocities are shown in this figure. The two-phase flow in a tube exhibits different flow boiling regimes depending upon the relative amount of liquid and vapor phases present there. So, it is the volume fraction. So, I have a liquid, number of bubbles which are present is the volume fraction. Note that the tube contains a liquid before the bubbly flow regime and a vapor after the mist flow regime. So, you can see here forced convection, you are flowing it. Then you see here liquid core, the liquid is on the core, the bubbles are on the surface. Then you can see bubbles in the liquid. So, now there is more bubbles in the, so the volume fraction of bubbles, they are all here touching the surface. Now, they are all through the surface. Now, what has happened? These bubbles get coagulated and they form a vapor. So, here it was liquid core, then it gets converted into a vapor core, and then finally, it gets converted into a liquid drop. Note that the tube contains a liquid before the bubbly flow regime and the vapor after the mist flow regime. The heat transfer in those two cases can be determined using appropriate relationship with single phase. So, here it is forced convection that leading to bubbly flow, then it is slug flow, then it is annular flow. Annular means it is annular like a ring. So, annular flow, and then finally it gets transited and it gets into a mist flow and a forced convection comes out here. So, the start, so this is what they say before the mist. So, note the tube contains a liquid before the bubbly flow regime and a vapor after the mist flow regime after this. So, you can see the coefficient of heat transfer. The coefficient of heat transfer is very high in the transition region and then it falls down. So, condensation heat transfer. The condensation occurs when a temperature of a vapor is reduced before its saturation temperature. We have seen this point. The film condensation. So, till now it was boiling. Now, we are trying to see condensation. Boiling was heated side. Condensation was vapor to liquid side. The condensate wets the surface and forms a liquid film. The surface is blanketed by a liquid film which serves as a resistance to heat transfer. So, this is like a liquid film getting formed. This is a plate. So, you can see a film which is getting formed. This taper. So, if you see the side view, it is something like this. This is a film. The dropwise condensation, film means it is continuous. Dropwise means at certain points there is a nucleating site and the droplet gets started here. The condensed vapor forms droplet on the surface. The droplets slide down when they reach a certain size. The droplet, what happens? The droplet also grows. After a certain heaviness, the droplet, it tries to fall down. So, the droplet slides down then when they reach a certain size. So, the droplet also grows from small, little larger, little larger, little larger, little larger, it grows. So, then after a certain time the weight is high, so it rolls down. No film is formed in the dropwise condensation. As a result, the heat transfer rate that is more than 10 times larger than the film condensation, because it forms, the surface area is there. So, the volume of the droplet is there. So, it tries to also evaporate. It also evaporates and then it goes away. So, it has droplet condensation has more efficiency, more heat transfer rate. So, if you see that this is a cold plate and then this is a film which is getting formed. So, if we try to draw the temperature profile and velocity profile, so you can see the liquid which is flowing from here. The liquid film starts forming at the top of the plate and flow downward under the influence of gravity. So, it is flowing down by gravity. Delta increases in the flow direction. Delta increases, the film thickness keeps increasing along the flow direction. The heat in the amount HFG is released. The heat is released during the condensation and is transferred through the film to the plate. So, from here to here there is a release of heat. The Ts must be below saturation temperature for the condensation to happen. So, T condensation to happen. The temperature of the condensate is Tsat at the interface and it keeps decreasing gradually to Ts. From Tsat it goes to Ts at the walls. Mass transfer. Till now what we studied was heat transfer, heat temperature T1 to T2, T2 to T1 and other things. Mass transfer is the study of the transfer of components in a homogeneous mixture from one phase to another coexist, or within the same phase from one regime of higher concentration to a lower concentration. Till now we saw heat transfer, now we are going to study about the mass transfer. The transfer of components from one phase to another is due to the difference in the chemical potential mu. So, it is like osmosis, the chemical potential mu of the component in the coexisting phase. The direction of mass transfer is from higher chemical potential to a lower chemical potential, where mu alpha y is greater than mu beta I. The components transfer I from alpha to beta phase. The chemical potential is a conceptual property. It can be expressed in terms of measurable properties such as mole fraction, concentration, pressure, vapor pressure, etc., etc. So, mass transfer plays a very important role. In processing industries, this plays a very important role. The importance of mass transfer operation in chemical engineering is profound. So, there is scarcely any chemical process which does not require either a preliminary purification of raw material or a final separation of products from byproducts, and for these mass transfer operations are commonly used, where they talk about the potential, chemical potential. Frequently, separation constitutes a major part of cost of the process. So, there can be two types of it: preliminary purification of the raw material, whatever it is, extraction, and then the final product you subtract. So, the processes which uses mass transfer are distillation. The liquid gets heated up and the vapor is formed, and the vapor condense, and then you get a liquid out. Next one is gas absorption. The gas is passed through and then you have absorbents. These absorbent absorbs whatever is whichever are the impurities into it, and the pure gas is released. Then the next one is extraction. The liquid, we add a solvent, so it is getting mixed, and then from the solvent then you try to separate the solute out, and then finally drying in air happens. That is also a mass transfer. So, I go back. Mass transfer is the study of a transfer of a component in a homogeneous mixture from one phase to another coexisting phase. Phase can be alpha beta, it can be liquid solid. Within the same phase, from a region of higher concentration to lower concentration. So, the phenomena which are seen are absorption, adsorption, removal of H2S from natural gas by adsorption with monoethanolamine and diethanolamine solutions we do, that is a mass transfer. Stripping of, removal of oxygen from water by the contact with the nitrogen gas is stripping. Distillation, we can try to do separation of benzene and toluene from the solution of benzene, toluene, and fractionalization of crude oil is also mass transfer. Extraction, removal of adipic acid from water using diethyl ether, removal of mercaptans from the naphtha by NaOH solution, absorption and adsorption, removal of odor, color and other materials using activated carbon. Adsorption is, or silica gel is also an adsorption. So, you have a gas, this is the gas bulk, then you have a gas film which is formed, then this is a gas liquid interface, then you will have a liquid film, and then you have a liquid bulb. This is called as absorption, gas liquid absorption. This is adsorption. Adsorption happens only on the surface. So, you have a solid bulk, you have a fluid bulk. So, there is a film formed and there is a sitting here. For example, a majority of the coating is done by adsorption. Majority of the tablets which are coated with color are done by adsorption. So, it is done by fluid flow. They do it by fluidized bed, but that is a different story. So, this is the mass transfer where gas liquid interface is there, gas solid interface is there. Gas liquid interface, absorption, adsorption on the surface. So, Na is equal to K times delta Ca. So, here Na is the mass transfer flux of a component A and K is the mass transfer coefficient. Na is the mass transfer flux of a component A, K is the mass transfer coefficient, Ca is the bulk concentration of A, and C suffix A is the equilibrium of the concentration of A. So, there are various forms we can try to talk about in the concentration moles per liter, partial pressure, mole fraction and mole ratio. So, here you have solute molecules and these are all solvent molecules. They get diffused and they form this. This is diffused evenly and equilibrium. So, then here what is there is you have a higher concentration, lower concentration. Here you have a solute through which it tries to move. So, here the mass transfer is dictated by diffusion Fick's first law. The diffusion is a process by which the molecules, ions or other small particles spontaneously mix with moving from regime of higher concentration into a lower concentration. So, this is given by the formula molar flux is equal to minus dA, these are suffix dA delta Ca by Cz. Suffix Ab is diffusivity or diffusion coefficient of the component A in B, then Ca is the concentration of A, Z is the distance fixed. First law is applicable on a steady state system Z. So, this is diffusion coefficient. It is almost like K times A. If you see the thermal conductivity formula, it is almost the same. So, here some examples are hydrogen diffusion into metals. This process can be described with either a mass transfer coefficient Ka or diffusion coefficient Db. The description with the diffusion coefficient correctly predicts the variation of concentration with positive and time. So, the hydrogen embrittlement is there, whereas the description of mass transfer coefficient predicts the variation only with time. So, this is very important. The description with the diffusion coefficient K correctly predicts the variation of concentration with position and time. Whereas, when you describe with diffusion coefficient with mass transfer predicts the variation only with respect to time. So, one it tells with position, the other talks with time. So, friends, in this lecture we went through what is a heat exchanger, what are the different types of heat exchanger. We saw in detail shell and coil heat exchanger, pipe in pipe heat exchangers. We saw plate type heat exchangers, how does it work. Then boiling, different types of boiling, pool boiling, flow boiling. Then we saw condensation. Then we saw different modes of heat transfer in boiling. Then various types of condensation processes what we do, and then finally we saw mass transfer. Mass transfer is very important when we are trying to look at coatings, adsorption, absorption, distillation. Everywhere mass transfer plays a very important role. As far as chemical engineering is concerned, mass transfer is a very important topic because it talks from a higher concentration to a lower concentration. So, these are the references which we have used through this lecture, and thank you very much.